Okay. So let's start with this talk about semantic attachments for domain-independent planning systems. And this is a method to generally integrate external procedures into classical planning systems. So why do we want to do this? There's a lot of real-world problems that actually contain sub-problems, like in the logistics packaging problem, or in robotics path planning or manipulation planning. And usually you can't really solve those with the classical planning only. The reason is that it might be either impossible because there's geometric calculations involved, or it's just unfeasible because there's a sub-problem which is high in computation, but there exist domain-specific solutions to solve these. And what we want to do is show a method of how to do this in general into a domain-independent planning system. So I have two examples here. The first one is transport. It's a well-known domain in symbolic planning benchmarks. Basically, you have a couple of cars driving around in the city. They should pick up packages and deliver them. And usually not all packages are the same. So one thing you can do when you have at least numeric fluence in the language, can add the size as a parameter and thus take care of size. This is valid for fluids, but if you look at real packages, they have a certain form and thus you can't really package everything. When you look at the grayish cube that you see at the bottom, the gray cube has a volume of 1, and the other two color cubes inside have a volume of 0.5. So basically, by volume they should fit, but as you can see, they don't fit at all. So we say that volume is just a crude approximation, and the better way would be to really respect the shape of the containers and somehow use a packaging algorithm to provide a correct solution. Second example is manipulation. So if you look at, for example, the blocks world, you can see it as an abstract version of robotic manipulation. There are objects, the blocks, they are moved around, but there's a lot missing from it. So there's no robot model, no kinematics, no gripper poses, no collisions, and there's an infinite table. So all this won't really work in the context of applying this to manipulation. But when you now could plug in a trajectory planner, then you would get a system which will give you a full manipulation planner. Now, there are two simple solutions that come into mind when you want to somehow combine planning with other algorithms. The first one is a top-down decomposition. And this basically means that you will have a somewhat abstracted symbolic description of your domain and use a classical planner to solve this, and then use the lower level algorithms to refine this plan, so to actually create an executable plan. The problem is when this abstraction doesn't model the whole domain, then you might get plans that are not executable anymore. So for example, this transport problem with the cubes that don't fit. And so a solution to that might be to handle a lot of contingencies in the low-level planners, but this still might not work out. The other way would be to use a bottom-up decomposition. So basically, you just look at what are the critical things and pre-calculate those, and then you can use this in a classical planning approach, and you will get correct plans. So an example is this can-load relation. In transport, you could just pre-compute this. The problem is quite obvious. You would have a lot of memory and runtime consumption, and the whole point of using a classical planner is not to search through the whole state space. So the idea is instead of computing those lower level things either after the planning in top-down or before in bottom-up, you will do this during the planning process. And there exist systems which do this already, but they're usually specific implementations to solve one domain or one problem. And what we want to do is a general approach, and this is called semantic attachments. The basic definition of that would be to have a predicate. This predicate has a semantic attachment being a procedure that determines the truth value of this predicate. So how this looks is normally when you have a planning system, you have your symbolic planner, and you have a domain description and a problem description. And when you plug those together, you get a symbolic plan. What we add to this is a semantic attachment, which has two parts. The one is the declarative part. This goes into the domain description. and it tells the symbolic planner how to use the procedural part, which is also supplied with the semantic attachment. And we have implemented two kinds of semantic attachments. The first one is a condition checker module, which is the intuitive kind from the original definition, and this basically just calculates truth values for grounded predicate. The second one is actually also quite important. This is an effect applicator. What you can usually do is symbolic effects you can model in the domain with condition checkers. You could do conditional effects and then use the condition checker predicate. What effect applicator modules are for is they can set numeric fluence, and this might be calculations which are out of an external procedure, and those might be the position of a robot after calling a planner, some things like these. And the important thing is what this allows us is to store even geometric information from algorithms in the full state of the planner, which can then later on be used by condition checker modules. This is an overview about the declarative part, and we based this on PDDL, and now did an extension to PDDLM for PDL with modules. And the idea is to really change as less as possible, so it really looks like PDDL, and this should be the idea. So if you look at the condition checker, you can see that it has a name, can load. There are two parameters, a vehicle and a package, and basically this looks like a predicate. So we add the keyword condition checker to it, and in the last line, a call to a procedure in a library. This tells the symbolic planner, once it runs upon this predicate, it needs to call this function to determine the truth value. For the effect applicator, it looks almost the same. So we have the name and two parameters. Again, the effect keyword, which tells it that this is an effect applicator module. And in the last line, the call to a function. What we add to this is a list of numeric fluents that are set by this effect applicator. So if you would use this putdown module in a manipulation action, then it would result in the 3 coordinates of the new for the object after the action is applied. This is how it looks in an operator. So basically this looks like a normal PDL operator. You have the parameters, and then there's a precondition which has a normal symbolic predicate holding. And then there's added to this another predicate, and this is can put down. So this checks if a robotic arm holding the object X can put it down on place Y, and this will run an algorithm which really does the planning. We mark this with squared brackets so the planner knows that this is a predicate that has to be evaluated and is not valid in the state. The same goes for the effect. There we have the put down, which is in this case an effect which would result in writing the new object position to the state. Okay, we have 2 implementations. One is in FF, which is I think well known, and the other one is in TFD, which is based on fast downward. Both planners are efficiently implemented, so we have a good start. And the integration of this semantic attachments into forward-chaining state space planners is actually quite straightforward. You just evaluate the states, and when you look at a predicate or an effect which has a procedure attached to it, you just need to call this procedure. One important thing is callbacks. Callbacks are used so that the modules have a chance to inspect the planner state. So the values of those predicates are dependent on the state, which is quite important in a lot of settings. One thing which is not so easy is that depending on the internal representation of the planner, it might be necessary to convert the internal representation back to PDDL, as the modules only have an interface in PDDL, and they shouldn't need to know anything about what happens internally in the planner. And what we expect from this is that ideally you can model a domain so that the full state is in the symbolic planner and the modules can be called independently. A simple example of how these callbacks should work. So if you're in the transport domain and you want to pick up a package, in this case truck 3 should pick up package A, then there would be the predicate can load. And basically what the planner would now do is it would call the module, and the module would now receive request to calculate the truth value of this predicate. And what the module needs to know is now what packages are already in the truck, because this makes it possible to then calculate the packaging algorithm and find a solution. So basically it will formulate a callback asking, for example, is package B in truck 3? So would write this predicate into a callback function and call it in the planner. And now the planner has to do the back translation, so it knows what value of what state variable in its internal state corresponds to this predicate being true. So it will then inspect the state and return the truth value to the module, which now starts its calculations and can then return the true value to the planner. Okay, one word about heuristics. So heuristics are quite useful in search, and the problem is that there are these module calls in between. So one very trivial solution is to use a simplified PDDL description. Remove the module or use something simpler, which is an over-approximation. But there's another possibility to do this, and the idea is to actually also use the modules during heuristic computation. So usually you can expect that running a manipulation planner or something like this as a module call is quite slow. But we reckon that whoever writes the domain-specific part of the semantic attachment also has probably a very good idea of how to simplify the problem so that we get an alternative computation method, which is really fast and an over-approximation. And the idea is then, when calculating heuristics, to use this alternative method. Okay, experiments. So we started the first experiment just to determine what basically the overhead is that we introduced by doing the module calls. And basically we choose the group planning domain because it contains a predicate available, which is used in almost any operator. And we replaced this with a condition checker module, which does nothing else than perform a callback to retrieve the truth value of this predicate. So it essentially does nothing different than writing the predicate in there. We then compared temporal fast downward and temporal fast downward modules. So temporal fast downward was using the original domain description, and the modules version, the one with the callback. As we have the same planner with the same heuristic, we can be sure that the exact same state space is searched to find a plan. And basically then we computed the overhead we introduced. And you can see, especially for the higher problem, it's about 30%, and the important thing is that it's bounded, so it stays the same, which is kind of what we expected from the implementation. And the overhead in runtime, we think is not so bad, because usually module computations will be quite complex, so they will dominate the runtime besides this one function call. Okay, the second one is the transport domain, which we've shown in the beginning, and basically we implemented the semantic attachment, which is a packaging algorithm. For efficiency reasons, we choose to do an under-approximation method. What that means is that whenever we say that the packaging is possible, it will be possible, but not the converse. So that means that we will get correct plans with correct packaging. The tricky things about these is that if you would have done this with top-down decomposition, you would have failed because you would have packaged too much into a truck. And bottom-up, well, you would have to compute the predicate can load for all possible subsets of the packages. And this scales very badly. And the third version we have done is basically we implement the manipulation domain. So in contrast to what we've shown in the paper, where we just had the simplified toy domain, we just implemented a trajectory planner as a probabilistic roadmap planner and plugged this into temporal fast downward with modules. And, well, basically then we had a manipulation planner. And this worked quite great. Okay, so to conclude, we've shown a general framework for integrating other planners and solvers into symbolic planning systems. And semantic attachments, the idea is to provide a more precise domain semantics. So you could use this for performance improvements, but the idea is really to provide solutions for domains that otherwise wouldn't have been possible to tackle. Another interesting thing you can do with this is you can easily link together multiple domain-specific solutions in one planning system. So you could take a path planner of a robot and a manipulation planner, just put them together under one symbolic domain, and then you would have a planner which is able to plan a path to a certain location and then pick up an object. Moreover, we have implemented 2 planners, and these are available, so we hope this opens up the possibility to easily create complex systems as we have shown in the examples. Okay, thank you. You mean the simplification? Well, basically, we'll do the same as we would do when we run the heuristic in a normal way. So when we just compute and walk through the state space, we just, instead of computing the real values of the modules, we set a flag to compute approximate values.
So you have a separate version of your module that is approximate?
Yes, exactly. And we think it's not a big problem because usually it means that you just leave out some computations. So for example, in the manipulation problem, we basically just check the collision for the goal state and then say it's okay, instead of computing a trajectory.
The way that you construct it, you're limiting yourself to forward search, right? Because your procedural attachment will only work in the forward direction. So if you want, you're also stuck with a heuristic that's computed in the forward direction. Do you have any idea how you could with that limitation?
Well, it might be quite complicated because it depends on the fact of what the modules compute. So as we did it with the forward system, it's quite intuitive what happens in a forward chaining system. For backwards, for some applications it might be possible to make a backwards module, but it's not so intuitive, I think, to computers. So right now we have implementations for forward chaining systems, but everything else is, well, not so trivial, I'd say. So we have no real ideas for this.
Why you don't include all the parameters that the module needs for the computation in the kind of call to the procedural attachments? Why do you need these callback functions? Couldn't you just give all the parameters that are needed for the computation in the statement? Because I'm also kind of worried that when I use procedural attachments, I don't really know which clues are relevant to that computation. But that might be quite useful in certain cases for some sort of, causal graph analysis of some sort.
Yeah, I think the main reason was that we didn't want to always convert the whole state from the internal representation to the PDDL representation that the module needs. But yes, we have also come upon the problem that in a lot of cases it's really relevant to know what is happening. So one example is that in the translation phase, usually a lot of stuff is thrown out because it's constant or seems irrelevant. And this sometimes happens with, for example, in transport with the package sizes. Nobody needs it but the module, and it's thrown out. So right now our solution was to do not allow to put anything out which makes the state a bit bigger. But it might be a good idea to just include the information, depending on what is faster.
Actually, I think I was going to ask the opposite question, which was how would you handle quantification in the callback?
It depends if they're in the module. We have no idea in how to compute this, but if it's just a quantification over modules, in the pre-computation they will just be expanded to multiple module calls.
Yeah, because I could imagine callbacks that make some kind of effectively quantified query.
We just allow callbacks for raw predicates. So
I have one more question, which is, it seems to me that because you're hiding some of the information from the planner, it isn't able to make some of the key decisions that it might need to make. So in the package packing example, if the planner is faced with the choice of packing, let's say, 2 small packages and 1 larger package into a volume that's just about going to hold them, because it doesn't really have access to the knowledge about the size, it might choose to put in a small package, which will be okay, and then the large package, which will fit. Now it can't fit the small package because it should have put it in first with the other small package. But the procedural attachments, or these semantic attachments, they don't know how to fix the plan either, because they're just saying, no, we can't do it. And the planner doesn't know how to fix it because it doesn't know what's wrong. So how do you get the communication between the specialized solver and the planner that only sees this abstract need to work so they can work together to fix this problem?
well, I think one problem about providing all information directly, so somewhere that the planner can see it, is that it might not be of constant size. So for example, for the packaging one, how many in attributes are used for this? This is dependent on how many are there in a problem. So we can't just write them down. But yes, it would be useful to have some kind of annotation or something like this to a procedure call, so that knows that the domain designer can somewhat define what are the predicates and fluents that are accessed by this module. And I think this would help, especially with things like the cursor graph.